Welcome back to the Data Professor YouTube channel. In this video, I'm going to show you how to do Principal Component Analysis, or PCA, in Python using the scikit-learn package. So without further ado, let's get started. So the first thing that you want to do is head over to the GitHub of the Data Professor, and then go to the code repository, click on Python, and then find PCA analysis. Click on that. And then you can follow along on this GitHub, or you could also download a local copy by right-clicking on the raw link, and then save link as, and then choose a suitable location on your computer. Or if you prefer to work on the Google Colab, you can click on the GitHub tab after you click on the Open Notebook, and then type in Data Professor, enter. And then look for PCA analysis. It's right here. Okay, and here we go. So in the last video, I've shown you how to build a simple linear regression model in this machine learning in Python series. And so today we're going to have a look at the Principal Component Analysis, or PCA. So PCA is an unsupervised learning approach which essentially compresses data from high dimension to lower dimension. And then the lower dimension data is called principal components or latent factors. By higher dimension, I mean that, for example, if you have 1,000 descriptors, you could essentially compress that down to like 5 descriptors or PC component. And then you're wondering, why would you like to do such a thing? Because when you're building a machine learning model using thousands of descriptors, it might take a long time. So if you could find a way to compress the data, but without losing important information, you could do that using the PCA approach. So all of the core information will be compressed into the principal component, or the PC, whereby the initial PC will contain the core information, while the last PC will contain the noise of the data. And so in this video, I'm going to show you how you can practically do that in Python using scikit-learn. So without further ado, let's get started. So you can see that today's tutorial will comprise of 5 essential steps. So the first step is loading in the data set, while the second part will be the actual principal component analysis. And the third component will be to create the scree plot, which will tell you about the variance of your data. And the fourth component here is to create the scores plot, which will essentially tell you about the distribution of your data samples. And finally, in the fifth section here, we're going to create the loadings plot, which will tell you the contribution of which factors or variables that are important for the data samples. So essentially, you could superimpose the scores plot and loadings plot together in order to see the contribution of which descriptor are important for which clusters of data. Okay, so let's begin. So click on the 14 cells hidden in order to expand it, and then we're going to load in the iris data set. So the first part is to load in the library. Okay, and then we're going to load in the data set into the iris variable. And then we're going to print out the feature names of this example data set. So we're going to see that there are essentially 4 input variables comprising of sepal length, sepal width, petal length, and petal width. Okay, and then now we're going to have a look at the output feature. And so we're going to print it out, iris.target_names. And so we're going to see that there are 3 iris species, setosa, versicolor, and virginica. And then the next step is to assign the input and output variables. So for X, we're going to assign iris.data, and for Y, we're going to assign iris.target. Okay, and then we're going to have a look at the dimension of the data, and we're going to see that the X dimension is 150 rows and 4 columns, and for the Y variable, we're going to have 150 rows because there are 150 flowers in the data set. Okay, so now let's proceed to the next step, which is to perform the actual principal component analysis. So let's click on the 16 cells hidden to uncover the cells. Okay, and then we're going to first start by loading in the library. So the first package here, we're going to use the scale function in order to perform the data scaling. And so the second function that we're going to use is decomposition. So essentially, this is the PCA. Okay, so we're going to load in the library. And then now we're going to perform data scaling. And here, as you can see, we're going to define that we're going to use 3 principal components. So n component is equal to 3. right? And as always, when we build the model, we use PCA.fit function. So PCA is the name of the machine learning algorithm, which we define to be the composition.pca function. And then using the .fit will essentially build the model, whereby the argument will be the input data, which is essentially the x variable. So notice here that we're using only the x variable because PCA is an unsupervised learning approach, meaning that it does not need the y variable or the class label in order to learn. So it's going to cluster the data based on the similarity and differences, so based on the eigenvalue that are inherently present in the data set. Okay, and 2.4 here, we're going to compute the scores value. And so the scores value will essentially be representative of the data samples. So we're going to use the PCA.transform function here, and input argument is x. So we're going to assign that into the scores variable. Okay, and in order to make it more readable, we're going to create a data frame called scores_df, and then we're going to use pandas.dataframe function, and as input argument, we're going to use the scores, because before doing this, scores is an array, as you can see here. Okay, so let me delete that. And by putting it in here, it's going to be converted into a data frame. And then we're going to name it as PC1, PC2, PC3. Okay, and after creating the data frame, it looks like this. Okay, so as a reminder, you can call the data frame variables like this, or like this. Okay, so you're calling it by the column name. Okay, so I'm going to delete this. Okay, and here we're going to add the class label into the data frame. And then here in this line of code, we're going to concatenate, or we're going to combine the data frame of the scores and the species together. And it's going to look like this. Okay, so we're going to have an extra column called species. And if you haven't yet watched the previous video where I talked about how you can combine the data frames together, so please have a look on the link up here. Okay, let's continue. And so we have already computed the scores value, and now we're going to compute the loadings value. So the loadings value will tell about the descriptor, and the scores value will tell about the data samples. And so for the scores value, because there are 150 flowers, there will be 150 values of the scores. And because there is 4 descriptor, we're going to have 4 loadings value, 1 for each descriptor. And so the third type of information that we're going to compute is called the explained variance. So the explained variance will tell us essentially what is the contribution to the percent variance of the entire model contributed by each of the principal components. So in other words, how much does PC1, or the first principal component, contribute to the overall variance of the data set? And how much does the second principal component contribute to the overall variance of the data set? And also, how much does the third principal component contribute to the overall variance of the data set? Okay, so we're going to have a look at that in the subsequent output. So here, the explained variance of the first principal component is 72.96%. And the second principal component will account for about 22.85%. And the third principal component will account for about 3.6% of the total variance. So if you add it up, you will roughly get 100%. So here you will see that the first principal component will contribute the most to the explained variance. So let's have a look at this visually. Uncover the 18 hidden cells, and then first thing that you want to do is import the library. Okay, and then we're going to prepare the explained variance data some more. So this essentially just returns the explained variance value. And then now we're going to add a origin value of 0, 0, meaning that x and y, we're going to have it 0. Because in the subsequent lines of code, we're going to create the scree plot. And the scree plot does not start from 0. So then we're going to have to manually create the 0 in order for it to start from 0. So you will see what I mean later on. Okay, and then in the next cell, we're going to compute the cumulative variance, meaning that at each point of the graph, it's going to show what is the cumulative variance of PC1, and then what is the cumulative variance of PC1 plus 2, and then finally, what is the cumulative variance of PC1 plus 2 plus 3. Okay, so in total, we're going to have 3. And in addition to the 0, 0 origin point, we're going to have +1. So it's going to be 4 data points. So you're going to see what I mean in the next few minutes. Okay, and now we're going to combine the data frame together. So we're going to combine the explained variance together with the cumulative variance. So now you see the importance of merging the data frame. Okay, so if you still haven't yet watched it, please have a look. Okay, so let's create the scree plot, shall we? So in this block of code, we're going to create the scree plot. And so this is the first attempt. And you will see in the subsequent attempt, we're going to add the cumulative variance. But in the first attempt, we're going to have only the explained variance. So using this block of code, we're going to create this bar chart. And as you can see, the bar chart is interactive. You can zoom in, zoom out, or if you double click, it'll automatically zoom out. And so this is created using Plotly package. And so this, we're going to use the Plotly Express. So it's going to be a bit different from the previous tutorial. And in this tutorial, the code of the Plotly Express will look a lot easier to work with. However, there are some limitations whereby more advanced or complicated plots will require the normal package of Plotly. Okay, but for this simple bar chart, the Plotly Express should be sufficient. So you will notice that we have already imported plotly.express as px. And then to make the bar chart, we're going to use the px.bar function. And as the argument, we're going to use the data frame df_explained_variance. So it is the data frame that we have created right here. And as the x value, we're going to use the PC. And so the PC column is right here. So it will print out the PC1, PC2, PC3 label. And in the y is the explained variance. And so the explained variance will be this column, the second column here. Okay, and then the text will be the explained variance. So we're gonna put in the text label, the value here, at the top of each bar. But notice that if we don't have this fig.update, it will look like this. It will look an awful mess, okay, as you see here, all of the digit decimals. But when we update the value, we're gonna tell it to limit it up to only 3 digit decimal. And then we're telling it to put the text outside the bar. Okay, so this is inside the update traces function. So it comes in handy. So we could customize the look of it. Okay, so this is the scree plot showing only the explained variance. And so we see that the first principal component contributed roughly 73%, and the second roughly 23%, and the third roughly 3.7%. Okay, so let's customize the scree plot further by adding in the cumulative variance. So in here, we're going to use the normal Plotly package. So not the plotly.express, but the plotly.graph object. And so we're going to import that as GO. And because we need the add trace function in here, and so we're going to create a multi-plot graph here. So the first component will be the scatter plot, which is the points here and the line. And the second component will be the bar chart, which is here, the blue bar chart here. And so this is the scree plot where you can see the cumulative variance in the green color here. And then the bars will represent the individual variance of each PC. Okay, and the curve here will represent the cumulative variance, where you have PC 0 or no PC at all is starting from 0. So no explained variance. Okay, and the cumulative variance at PC 1 is the same as having only PC 1. So it will start at 73%. And then the cumulative variance will add another 23% to become roughly 95.9%. Okay, and then you have the cumulative variance of PC1, PC2, PC3, which would then become almost 100%. Okay, so let's hop on to the next cell. And so in this block of code, we're going to create the scree plot of the cumulative variance and the explained variance separately. So on the left, it's going to be the cumulative variance, and on the right, it's going to be the individual explained variance. And so we modified the code a little bit by having figure equal to make subplot, row equal to 1, column equal to 2. And then in here, we define that we want the scatter plot to be row 1, column 1. And for the bar chart, it's going to be row 1, column 2. Okay, and you could modify this to be 2 rows, 1 column, up to your desire. So maybe that could be your homework. So actually, that's a good idea. Try that out and let me know if it works or not. Okay, so let's continue. And now click on the hidden cells for the scores plot. And now we're going to have a look at how we can make the scores plot. And so here we're going to use the Plotly Express. So let's load in the library, and then we're going to create a basic 3D scatter plot of the three principal component, PC1, PC2, PC3. So here we're going to use the px.scatter_3D function, and as the argument, we're going to have the name of the data frame. So the data frame name is df scores. And then the column name that we're going to use to be X will be PC1. And for Y, we're going to be PC2. And for the third dimension, or Z, we're going to have PC3. And then we're going to have data points colored by the flower species. And so we're going to have color equal to species. And so because we have three species, versicolor, virginica, and setosa, it's going to create three different colors for each of these species in here. And so if you hover your mouse over the data sample, you're going to see exactly which flower species it belongs to. So the bluish purple will belong to the setosa, and the green will be virginica, and the red will be versicolor. So we can see here that the setosa is rather separated from the versicolor and the virginica, and that the versicolor in red and the virginica in green, they're quite similar because they share similar space in which some of the data samples are overlapping. And if you have already performed some classification model building of the iris dataset, you will see that the versicolor and virginica in the confusion matrix will have cross prediction between each of these two classes, meaning that there will be false positive, whereby a flower that is actually a virginica will be predicted wrongly to be a versicolor, and a versicolor flower will be incorrectly predicted to be a virginica. Okay, and the purple color here is the setosa. Okay, so let's customize the scatter plot a bit, shall we? So in here, we're also going to assign different symbols for different flower species. So with the option argument symbol equal to species, and so different species will have different symbol. So you see that setosa will be circles, and virginica will be squares, and versicolor will be diamonds. And notice that we also added the opacity option here to be 0.5, and so it's a bit translucent, and data samples that are overlapping will be darker colored. Okay, so this helps you when your data is stacking on top of one another. So more dense area will be seen clearly if you add the opacity to it. Okay, and here we also made the figure to be more tight, meaning that the left, right, bottom, top will have zero margin. Okay, so you notice that the plots are bigger when you compare it to the previous one, much smaller. Right? So you can experiment with this. I mean, if you don't want to use this tight function here, you just rerun it again and you'll see that the plot is smaller. Oh, it won't show because it needs the fig.show function. Okay, here we go. So let's see if we take it out. Will it be bigger? Okay, it's slightly bigger. At least no white margin, right? And so notice here that on the last line of this cell, you can change the theme of your graph. So if you don't like the default of Plotly, you could change it to other themes. So let's play around with this. So let's use Plotly white. Okay, and notice that the gray background is now gone. Or if you want to try Plotly dark. Okay, it's black color here. Or if you want to try ggplot2. So this is going to imitate the one in the R package, ggplot2, or even Seaborn. And then simple white. Okay, so you don't see the gray color at all, or just simply nothing, none. Okay, very minimalistic. If you comment this, then it'll just be the Plotly default. Okay. So let's hover over to the next part, loadings plot. Let me close that. Okay. So let's start by making the loadings plot. So run the block. Oh, okay. df loading is not defined. Let's have a look. Where is df loadings? Right here. Oh, probably I did not run it. Okay, so notice here that you have 3 principal components and then you have 4 descriptors, so 4 loadings value, as I mentioned already. Okay, and now let's run it again. Okay, here you go. So this is the loadings plot, and so you see the distribution of the descriptors. And so I mentioned previously that you could even overlap, meaning that if you have it shown in the same viewpoint, you will see that which features are important for which data clusters. Okay, so we have it ordered here. PC1 on the right, PC2 in the middle, PC3 on the left. Okay, same ordering. So you're going to see that on the far right here, it's going to be sepal width. And then on the far left here, it's going to be 3 variables, which are petal width, petal length, and sepal length. So sepal width apparently is more important for the setosa flower. Okay, and the remaining 3 descriptor here are important for the setosa and the virginica. Okay, so you can see which factors are important for which data clusters. So this will come in handy when you're interpreting the data. Okay, so congratulations, you have now successfully performed principal component analysis. And so please play around with this notebook, and you could try by importing different data sets and then looking at the scores plot, loadings plot, and try to superimpose the scores and loadings and interpret the meaning of which feature are contributing to which data cluster. So give it a try, modify the code, and then upload it to GitHub, and so start building your portfolio. Okay, so have fun. Thank you for watching. Please like, subscribe, and share, and I'll see you in the next one. But in the meantime, please check out these videos.